correlation physics should look like. So what this has been discussed ad nauseum in this conference, but let me just go through the fundamentals of this Hamiltonian once again. So what I have is a hopping part, essentially that is controlled by this hopping integral T, right? That allows the electrons or fermions to hop from one side to the other. You have a chemical potential that essentially determines your filling, and then you have an on-site Coulomb interaction that is essentially gives a penalty if you have two electrons sitting in the same site. Okay, so the thing is that since this is a disorder part of the conference, we have to start putting in disorder here. So there are many ways of putting in disorder. One of the standard ways of putting in disorder is having a random potential Vi sigma, and so that at each site the electron sees a different potential or a different chemical potential in some way. Okay, the way we are going to do it is that we are going to draw the potential from a distribution, a box type distribution, and so far as this slide is concerned, this Vi sigma is felt by both the fermions, right? Both the upspins and the downspins see the same disorder potential. Now, so this is a standard model. So this is in some sense a standard model of strong correlations, and we are going to ask what happens to this model, or whether as you tune on U and delta, whether one could effectively have a metal-insulator transition in this system. So before we go on to a case with a U, let us look at what would happen if we have U set to 0, if you're dealing with completely non-interacting particles. So if that is the case, then you get this famous picture. Now everyone who has studied strong correlations were taught this, maybe when you're is that a question? Okay, sorry. Yeah. So yeah, sorry. Yeah. So this is the famous gang of 4 result, and the famous gang of 4 result can be described as follows. So what you want to do is to look at what would happen when you are in the large conductivity limit, right? When you are in the large conductivity limit, G is much greater than 1, right? If you are in the large conductivity limit, G is much greater than 1, and so you would expect Ohm's law to hold, right? So essentially, you should have, as far as your conductivity or conductance is concerned, you should have the Ohm's law to be valid. So the conductivity should go as conductance should go as conductivity should go as some L to the d minus 2. So, and then the question that you would want to ask is, what would happen in the small g limit? So in the limit where the disorder is very strong, you would expect that the states are localized, strong Anderson localized. That means that your wave functions have essentially a exponential spread only, correct? Has an exponential spread only, and then what would happen is deep down, right, you should have an insulating state. Now the question is, what would happen to this system as you keep increasing the system size? So what this curve tells you is, no matter what happens, if you're in small enough dimensions, that is in 1 and 2 dimensions, you will always flow to an insulating phase. Okay, so the question is, the point is that no matter what you do, you can never have a metal insulator transition because all states are localized. Okay, now in 3 dimensions, of course, there is a fixed point that essentially controls the metal insulator transition, and the question that we want to ask is, if at all we add interactions to this system in 2 dimensions, for instance, can we delocalize these localized states? So this is actually important, that all states are Anderson localized, right? And the question that we want to really ask is there a possibility of switching on a Coulomb interaction, and will these Coulomb interactions actually help us in delocalizing these Anderson localized states? Okay, so the reason why the reason why this actually became very important was this set of beautiful experiments by Kravchenko. And these experiments were on very high mobility samples of silicon MOSFET. So what he saw was that when the density was the density of the electrons was lower than a particular critical value, you would essentially see a metallic phase, and in the other regime you would actually see an insulating phase. So these curves are essentially something these curves are essentially something that is close to the separatrix that essentially demarcates a metallic phase from an insulating phase. So this is resistance as a function of temperature. Of course, this always opens up the possibility that this is some sort of a transient behavior, and finally as you reduce the temperature you will effectively get these things to upturn. So these curves are all metallic. As you can see that the conductivity essentially goes down, the conductivity essentially goes up, or the resistance goes down, whereas all these curves are insulating. So, and you keep changing NS, the density, and at some critical density you essentially see a change in behavior that is an indicator of a metal insulator transition. Okay? So they have actually gone on and then done better. You can essentially collapse all these curves onto two universal curves, essentially trying to justify that there might be a metal insulator transition in here. Okay, so this was a huge surprise, and it was a huge surprise because earlier on people had actually looked at looked at field theories that would essentially include the effect of electron-electron interactions in a nonlinear sigma model sort of framework. But if you do, so this nonlinear sigma model sort of framework essentially tells you how the soft modes in the system, or the diffusion modes, essentially interact, right? And what they found is that when you did the renormalization group equations, you essentially found this set of coupled differential equations. Here psi is something related to the temperature. It could be related to the length scale also, but in this case it's related to temperature. So what they found is that, of course, early on this 2 probably dominates, and then what happens is as you keep doing the RG, as you let t goes to 0, this term essentially starts picking up, which means this term actually starts dominating. Then this guy essentially goes through a maximum, and then the resistance starts to decrease. Okay, but so that essentially is an indicator to the fact that you might actually have what is it called? You might actually have a metallic phase. But there was a serious issue with this. The problem is that this gamma 2, which is some sort of strength of a triplet interaction, kept on increasing, and it went to very large values at a finite scale for psi, which essentially meant that this perturbative RG probably went away from the regime of its validity. Okay. Later on, this runaway flow of this gamma 2 was essentially interpreted as as to do with a ferromagnetic itinerant ferromagnetic susceptibility diverging, and that has to do with the runaway gamma 2 essentially had to deal with having instability towards an itinerant ferromagnetic state. That is how it was reinterpreted. Now, what happened is, of course, this set of equations, of course, as I just told you, was not able to completely describe the fact that there is a metal insulator transition, even though there was an indicator that the things could work out. I mean, that things could go metallic. So what happened? Finkelstein and Punnus, or Punnus and Finkelstein, essentially took over this description, added the fact that silicon has some Wally degeneracy, and in the limit of large number of Wally degeneracy points, essentially showed that there could be a fixed point, and this fixed point could actually describe a metal insulator transition of this sort. But there was definitely an issue here. This entire calculation of of Punnus and Finkelstein was based on the fact that you have a large n sort of calculation, whereas here the number of Wally degenerate points was 2. So it was not very clear whether this would actually help. So my talk is essentially of the is of the same genre. But in my case, what I'm going to do is do the following thing. That is, I have the same Hubbard model, right, as we have discussed so far, with the same sort of hopping and interaction U. But now what I'm going to do is do something very, very weird, and that is I will see to it that only one species of fermions see the disorder. In my case, it is the down spins that actually see the disorder, and the up spins don't see it. The motivation behind this seems to be that you can construct these things in cold atomic systems, but I'm not going to get into it because I myself am not very clear on this. So this was first studied in a DMFT framework by the group of Bychuk, Folhart, and a student. And what you see is this following phase diagram that actually plots interaction U as a function of the disorder on the y-axis. So for small interactions, of course, you can see that there is a metallic phase where both the spin species, the up and down, are itinerant. Okay, as you stay at small interaction and you go up, it's infinite dimensional. So it's DMFT. It's DMFT. Even in infinite dimensions, is it? Okay. It's not exact anywhere. Okay. Okay. So as you will come to see that our results actually differ from these. So what happens is if you sit at small interactions, and you drive up the disorder, then essentially there is a transition to what they call spin selective localized state. Now this is a strange state where only one of the species, that is the species that sees the disorder, gets localized, and the other one is completely free. I mean, or sorry, not free, but itinerant. Okay, so here the downspins are localized, but the upspins are localized, because in this case they put the disorder on the upspins, but it doesn't matter. The upspins are localized and the downspins are completely itinerant. As you increase the interaction strength, of course, you essentially go. You sit a small disorder, you increase the interaction strength, then you go through a Mott-Hubbard sort of transition, and this, of course, is where the coexistence regions actually shrink. This can be actually understood by disorder effects, because once you have disorder, then it essentially tends to suppress the first order transition, and that's possibly the reason why this goes through. Now over here, what happens is, since one of the fermions are completely localized but Anderson localized, and the other one is moving around, this actually represents quite a bit the Fallikov-Kimball model. So then there's a transition at large value of disorder and large values of interaction that essentially is something like a Fallikov-Kimball type transition. Okay, so now what I'm going to do is, since this was a DMFT type of transition, DMFT type of paper, what I wanted to do was to look at this transition in the framework of a quantum Monte Carlo scheme. So this is where Sashi came into play, and Sashi essentially did this calculation. And what we do is, now I'm doing QMC, and I'm looking at the conductivity as a function of temperature. So the first thing I do is I switch off the interactions. So if I switch off the interactions, then essentially everything should look Anderson-like, right? In dimensions 2. Yeah. No, it is QMC. Now, detrimental quantum Monte Carlo. Yes, the same thing. So we actually learned this from Professor Raimondo's review article, and that was, I think, the best review article that anyone could use to learn QMC. Even I understood it a bit. So anyone can understand this. So here what you have is the u equal to zero limit. So we just want to check if our calculations are actually consistent and whether we have got things right. So what we do is we essentially set at u equal to 0 and tune the disorder. So as you can see, effectively as the interaction strength, as the disorder strength actually increases, the tendency to localization essentially also increases, right? So it's very clearly seen for this low disorder thing. You actually initially have this upturn, and then the Anderson localization kicks in, and then the conductivity actually starts going down. Sorry? Through the beta tau in your theory, right? I mean, I write it in an action.
Just thermally populating some states.
Yeah. Of course, we are not plotting the upspins because they are completely free. Because the only way that you can actually see disorder for the upspins is if it talks to the downspins. Okay. So now what I do is I essentially put u not equal to 0, right? And I actually look at what would happen to the conductivity as a function of temperature. And I have to be very specific now. So I am right now sitting at a half fill lattice, and this is going to be actually very, very important for me. Okay, so I am sitting at a half fill lattice, and I am actually driving this temperature, the system in temperature. So what I do is I sit at a particular value of disorder, for example delta equal to 2, and I tune my interaction strength. So as you can see, what seems to happen is that as you increase the interaction, as you keep increasing the interaction, the tendency for the spins to localize becomes stronger and stronger. So the blue curve is the one with the largest interaction, the smallest, and the red curve is for the largest. So the insulating behavior becomes much more pronounced as you keep increasing the interaction strength.
What are the units of?
It's in some terms of beta, some 1 by temperature. In terms of T, so in terms of T, so T is I put equal to 1. The systems are 10 by 10. So that's the maximum we can go with the resource we have. I mean, Sashi could possibly do 12 by 12, but we haven't done it. So that's a good, yeah. So as you now what happens in the spin up sector, which actually in the Baird theory does not see any disorder. In the spin up sector, what happens is because of you switch on a U, then the spin up guys also see the disorder, and as you can see, they also start localizing, right? So at half filling, and as you increase the interaction strength, the localization becomes, or the localizing behavior becomes more prominent. So as you can see, at half filling, at moderate or small values of disorder, everything seems insulating. So you get back whatever we thought we should get back, and we get back all we thought what we should get back. And very soon I will show you some results for the density of states, and then it becomes clear why this is so. Sorry. So this is exactly the same plot, but a different value of disorder, and the entire thing essentially gets repeated. That is, as you increase the disorder strength, as you increase the interaction strength, things look more and more insulating, right? So what now I want to do is to go away from half filling and see if there are any differences, right? So what I want to do is to go away to say some quarter fill lattice, do the same experiment, and see if things change. And here is the first thing. So what I'm doing is I sit at a fixed u, sit at a fixed value of u, and change the disorder. So as you can see, as you sit at a fixed view and change the disorder, things become more and more insulating as we expected. Now we go, that is for the downspin guys. Now we go to the upspin fermions. The fermions which have seen no disorder initially, but sees disorder once you switch on a U, and again do the same process. I sit at a fixed U, so and change the disorder strength, and what I see is possibly a metal-insulator transition that is driven by disorder, right? So as you can clearly see from here. So this, of course, is not my main result. So if this was the case, then I wouldn't be so happy. Now I go to the other limit, and this is my important slide. So now what I am doing is I sit at a large value of disorder, okay, an extremely large value of disorder, and I essentially tune U, Okay, and as you can see, when u is 0, everything looks insulating. Now let's contrast that with some u equal to 7, which is a very large value of interaction. And what you can see is that as you tune on u, there is a tendency for the system to delocalize. The conductivity actually has a sharp upturn. Now whether this sharp upturn is actually a metal-insulator transition, I do not know, but it is a very sharp upturn, right? And what is interesting is this upturn, the value and temperature where this upturn actually happens actually goes up with increasing interaction strength. Okay, so this we believe might be an evidence of a probable metal-insulator transition that is driven by interactions. Now, if you look at the spin-down species, sorry, the spin-up species, then it's a good metal here, but as you keep increasing the interaction strength, then what happens is it becomes just a worse metal. Okay. Now, accompanied with this rather remarkable upturn, we actually see another feature is that this system essentially develops a polarization, right? And how does this polarization come away? And this only happens away from half filling. How does this happen? So essentially you have your non-interacting bands, right? In a single particle picture, when you switch on interactions, sorry, when you switch on disorder, then say the downspin carries a disorder, it essentially effectively broadens. Now you start filling up your states. Then what happens is there are enough states here that you first start filling up the downspin guys and then start filling up the upspin guys. This essentially leads to an imbalance, and essentially you get effective polarization. So this upturn is effectively also comes with a polarization where the number of downspins essentially increases as respect to the number of upspins. This also leads to a susceptibility which actually does not diverge, which is actually I think kind of crucial. I'll come to it in a bit. This is actually crucial, that the susceptibility never diverges. It saturates to a finite value, but the value of the susceptibility increases with increasing interaction strength. Okay, it almost is like that the polarization actually essentially cuts off this divergent susceptibility, so to speak. Now, what might be happening? So what we did is we essentially looked at the density of states, and we compared the density of states at the filling fraction of for a half fill lattice versus something with which is at the quarter fill lattice. So here is the density of states at the Fermi level. So what you see is as you switch on an interaction in the half fill lattice, effectively a Mott-Hubbard gap develops. Right? So there are no states over here that can effectively conduct. Whereas away from half filling, what happens is there is the Mott-Hubbard gap is really not active. So at the Fermi level, there are still states that are at that in the absence of an interaction are localized. But now what happens is if you switch on an interaction, then the system can essentially effectively delocalize, or these Anderson localized states can actually delocalize, and that is possibly what we are seeing in our system. So what we believe is that this is the case in all filling fractions away from half filling. So we have done this for some other filling. We have done this away for some other filling fractions too. So one more typical example where we essentially see this sharp upturn. Our bet is that this would happen sufficiently away from half filling. We will always see this, but sufficiently away from half filling, the problem, we can't do calculations because the sign becomes pretty bad for us. So that's why we can't do this. So we have done it for a few filling fractions, and in these filling fractions we actually see this. Actually we have done this for quarter and this 0.4. And we actually see the same sort of behavior. So how much time do I have? 5 minutes. Okay. So the important thing for at least that we believe is the fact that is the fact that the susceptibility for example does not diverge. So it could very well be that if you remember the Finkelstein flow equations that I had written down, it could very well be that associated with this susceptibility there is an interaction strength, and instead of that interaction strength running away because of the fact the way we put in disorder, it could very well be that this forces this interaction strength to saturate to a finite value, and this could possibly then lead to a metal insulator transition that could possibly be explained in a Finkelstein-Belitz-Kirkpatrick sort of field theory. So what we have actually shown over here is the fact that in real if I take Hubbard model with spin selective disorder, then what I find is that there is at half filling all states seems localized, and there is no possibility, it doesn't look like there's any possibility of a metal insulator transition. Away from half filling, what we have seen is that there is a metal insulator transition, or there are a couple of metal insulator transitions that one could think of. One is this nice U-driven transition. One is this nice U-driven transition that I've just shown, where the conductivity shoots up rather dramatically. The other one is a metal insulator transition that in the minority spin sector, or in this case the upspin guys, and they're called the minority spins because after you put in disorder, right, the number of downspins which sees the disorder at the bar level actually increases, and the number of upspins that does not see the disorder at the bar level decreases. In the minority spin sector also you can have a metal insulator transition that is purely driven by disorder, right. Now the thing is the thing is that I would like to understand. So now what is the outlook that we have over here? So I want to really understand, as someone said, I have only a 10 cross 10 system, right? And I want to really understand if I want to really understand if this if this transition is a real transition or just some sort of a renormalized effect, where the disorder, because of the presence of interaction, the disorder actually gets downward localized, downward renormalized, and since the disorder becomes downward renormalized, effectively the localization length becomes larger and larger, and hence things look metallic kind of. But if you really are able to go to larger system sizes, then you will again see insulating behavior. So this is something which I do not know, and if I really want to know if this is actually a metal insulator transition, I would possibly want to try to develop a field theory which actually shows this is true. Okay, so that's something that we are thinking about, or if there are other ideas to actually show that this is indeed a metal insulator transition or not, I would be more than happy to listen to you. So thank you. Yeah, 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 yeah. Yes, I know this.
So they also had the tendency for this to
so their results are on with random hoppings. The Tij is a random. It's not a random chemical. It's not a random potential. Right, and of course, yeah. So of course, yes, you're completely right. Dentinier, Trivedi, and Skeletor really showed a sharp upturn, and if I don't remember, that was also an 8 cross 8 lattice, right?
Yeah. And in the same line, so I mean, they had an upturn.
Yeah.
Your upturn is very sharp.
It's very sharp.
Having a superconductor,
yeah, that I have not. But yes, I agree. But we have not thought of that at all. Because I mean, to get a superconducting state, somehow my U should be attractive, and I don't know if the disorder is strong enough to come in and renormalize my U.
So have you tried to
No, we haven't done. We haven't done it. We haven't done it. Because I just, at least the way I think about things, I never thought of this going superconducting. But this is a so can I say something more on this? May I?
Very short.
Yeah, very short. We are also doing this with the disordered case, and we are just writing it up. Sorry? Yeah, so that could be the reason why I'm getting a delocalization, right? No, it has. So the Kravchenko results I have used as just a motivation. So I am not saying that my calculations here are Kravchenko's or will explain Kravchenko.
There are systems where it turns out that the metal-insulator transition coincides with the ferromagnetic.
Right, right.
And in those systems, the resistance can actually go up
Right.
into the ferromagnetic phase rather than down.
Yeah.
Not counterintuitive.
Yeah, it is counterintuitive.
But that's due to disorder. That's adaptive to essentially different localization effects in the majority and minority.
Right. Yeah, the Kravchenko system. I'm not trying to explain the Kravchenko system. Yeah, yeah, because that doesn't have this sort of disorder, right? I mean, in fact, I don't think that any solid state system I can make with this sort of disorder. I hope. I mean, yeah.
So I would like just to make a comment to that question. The first comment is that, even though I understand this is not necessarily applied to be a theory for Kravchenko, but there's something specific about Kravchenko's experiment. And that's the fact that this range where you see these curves nicely spreading out like this, this starts at the scale which is comparable to the Fermi energy, which is a much higher energy scale than where you would assume some interference processes and things like this Finkelstein theory to work. And indeed, if you talk to Alex Pinus in particular and others, you can estimate where is the so-called diffusion regime, where this kind of corrections would apply, and there is a high temperature regime where they do not.
Okay.
Many experiments, in fact, mass enhancement and later showing correlation effects were done in the ballistic regime and not in the diffusion regime. And a large fraction of these temperature dependence where you see this spreading out is actually the diffusing regime. So, it's pretty clear even to the authors of this theory that this is not possible to explain in this framework at all. Right? So that's one comment. This is completely unrelated to your work. And my question is that in this model and this system, you can also ask the same question. Where is the diffusing regime? Because at higher temperature, you put Hubbard U, there is inelastic scattering. That will introduce a cutoff to diffusion. And so forth. So it's a fair question to ask.
I know.
Diffusing regime, where is the ballistic regime, right?
Yeah. So the only way I can answer this question is I didn't think about this at all. So, but this is a good question. We didn't think about this.
Did you look at the cross-conductivity? So if you apply a field at one species and look at the
No, we didn't. It's a sigma up down, right?
Yeah.
If we haven't done this, but you need to be able to connect these two, right? At the bare level, they are actually unconnected. The Green's function is just this.
If you apply a force on one
Yeah, we haven't done this. No, we haven't done this, but yeah. By using this Kubo type formula, and then instead of doing this analytic continuation, we use this approximation, the Nandini, and we use the approximation exactly. That is the reason I don't have any results for the clean guy, because you expect this approximation to break down, in a real Fermi liquid. So and that's why we kept disorder at some large value and then did this. So we didn't do this.